So, we start with some examples. When the Lagrangian is given, okay, then the equation of motion are this one. When I is varying from 1 to n. So in order to understand what we are doing, we need to make some exercises. So what we need to do is we need to choose some Lagrangians and see which are the equations corresponding to a given Lagrangian. You will discover that a lot of equations which you have already seen can be found suitably choosing the Lagrangian. Okay? So we'll start understanding slowly the power of this postulation scheme. So, I will not do all calculations. I will leave to you to make the calculations. Okay? And I give you some hints. So, for instance, let us consider a 1 degree of freedom system. So the only Lagrangian parameter is the variable x. And let us choose as a Lagrangian what we already did. 1/2 kx squared minus 1/2 mx dot square. We did the calculations. Please repeat these calculations. In this case, I is equal to 1. So you get only one equation. Q1 is equal to x. And what you get out of this? The equation of harmonic motion. The aim of the 2 lectures of today is to prove that actually in reality this is not a very particular case. Harmonic motion are all the motions which can occur in the neighborhood of an equilibrium position for every Lagrangian. I try to be more precise. I will tell you what it is an equilibrium condition, an equilibrium position. An equilibrium position for a Lagrangian is a configuration such that this motion is a solution of the equation. So remaining in QE for every time instant is a solution of Lagrange equation. This is an equilibrium. This is an equilibrium configuration. Okay? Then imagine this is a kind of Lyapunov definition of stability of equilibrium. Imagine to have Q T0 equal Q E plus a small delta, and imagine to have that Q dot with delta, okay, let us call it this way. Delta is an element of Rn, and the norm of delta is small delta, which is an element of R plus. So you are perturbing a little bit the initial configuration, and then you assume to have that Q dot T0, the Lagrangian velocity of your system, has a norm which is smaller than delta. Okay? We say that QE is an equilibrium, a stable equilibrium configuration for your Lagrangian system, following the definition of Lyapunov, if for every t the norm of Qt, which is the solution of this, minus QE is smaller than epsilon. Of course, I must say, for every epsilon there exists a delta such that this implies that. This is the definition of Lyapunov stability. Okay? So, for every small number, there exists, of course, positive. There exists another small number, positive, such that if I place my system in a configuration which is close to the equilibrium, and if the initial velocity is small, of course Q dot is an element of Rn, so I must calculate the norm of this in order to say exactly what it means that it is small. Okay? Then I am assured that for every subsequent time instant, the system remains close to the equilibrium configuration. If you want to remember this definition, think about this system. You have a metallic guide and you have a small ball with a hole inside, and the ball is sliding on this guide without friction. Okay? So there is a perfect surface, so the interaction between the ball and the guide means as the only effect of obliging the ball to remain on the guide. This is an equilibrium configuration for your ball. Why? Because if you decide that the motion has to remain at a distance epsilon, okay? You can place the ball at a distance delta from the equilibrium. You can give a speed, a velocity smaller than delta as initial velocity, and the motion of this ball remains always inside this epsilon neighborhood of the equilibrium configuration. Okay? So this is the intuitive interpretation of this formal definition. By the way, I hope that you are not afraid of epsilon delta's definitions, because otherwise you are not mathematicians. Okay? Now I can try to tell you in better details what I said before. What I claim is that in the neighborhood of every equilibrium stable configuration, for every Lagrangian system, the motion is always the sum of many harmonic motions. So you believe that when you are studying this, you are studying a particular case. Actually, this Lagrangian is the Lagrangian of every small amplitude motion in the neighborhood of an equilibrium, a stable equilibrium configuration.
So we can have multiple equilibrium points? That is what you're saying?
What it means, multiple equilibrium points?
Like you're saying every equilibrium point. So how many equilibriums do we have?
In general, for a system, a Lagrangian system, look at this drawing. You have this equilibrium, and this equilibrium. However, so with this simple system, you have 3 equilibria. This is a stable equilibrium. This is a stable equilibrium, and this is unstable. Why? Because if you move a little bit the initial position of your system here, it falls down, it goes up, so it goes very far. So even if you place it very, very close to the equilibrium configuration, the system has an evolution which goes very far from the equilibrium. So, in the classification which we must use, first we define equilibria. An equilibrium configuration is a configuration in which this constant motion is a solution of the Lagrange equation. Okay? This is an equilibrium. If you place your ball here, exactly in the maximum, it remains there. If you place your ball here in the bottom of the valley, it remains there forever. Okay? So you have different kinds of equilibria. Why? Because a small perturbation of the equilibrium at the top results in a motion which goes very far, while a small perturbation of the equilibrium at the bottom results in a motion which remains confined. Of course, if delta is small, which remains confined in the what is called attraction basin of that stable equilibrium. Okay? And in general, there are many equilibria for a given Lagrangian system. Okay. Now let us try to be more, I repeat what I wanted to say another time. I call a small motion in the neighborhood of a given stable equilibrium a motion whose amplitude is suitably small. Of course, this means something to be specified better in what follows. Okay? And what I claim is that for every Lagrangian, so for every Lagrangian belonging to a certain class we will describe later, okay, for every Lagrangian, the small motions in the neighborhood of an equilibrium configurations is the combination of exactly n harmonic motions. So if you have a system with n degrees of freedom, the small motions of this system with n degrees of freedom in the neighborhood of an stable equilibrium is the composition of n harmonic motions. as this is a very important subject of great importance both in mathematics and in every applied sciences, I want to show you the mathematical reasoning needed for proving this, with a degree of rigor which is not so outstanding. This is written in the book of Levi-Civita. So this is what I will tell you is written in a book which has been very important in the history of mechanics. Okay, I found it in every library in the world, even if it is written in Italian. Okay, before proceeding, I give you some exercises. Better I start doing some calculations so that you become familiar with what we are doing. Usually, kinetic energy, what is kinetic energy? I don't know what is kinetic energy. It's a name. We introduce a quadratic function of the Lagrangian velocities in this way. Summation over hk of 1/2 ahk function of q dot h q dot k. This is a homogeneous quadratic function of the Lagrangian velocities. ahk is a matrix which is assumed to be definite positive. I hope you know what it is, a definite positive matrix. And this matrix may, in general, depend on the variables q, on the Lagrangian variables q. Okay? This is a possible kinetic energy for our system. I don't know what is a kinetic. For the moment, it's a name. Okay. In general, potential energy, which is denoted with U, is a function of only the variable q. I don't mean that every Lagrangian is built in this way. I simply want to give you an example. Okay? Hamilton studied a set of systems in which the Lagrangian is given by u of q minus t of q dot. An Hamiltonian system is often assumed to have this Lagrangian. So you have a function of the q only, and a function which is quadratic in q dots with the coefficients depending on q's in general. Okay? So let us try to see how the Lagrange equations look like for this particular class of Lagrangians.
Q raised to h and q raised to q?
Sorry?
Q dot raised to h? Is it raised to the power?
No. This is a summation. This is a Dam index. And I'm using Einstein notation. Indices on which you have summation are repeated, one up and one down. I wrote summation over h and k. Look, this is a shortcut for 1/2 a11 q dot 1 q dot 1 plus 1/2 a22 q dot 2 q dot 2 and so on. And I am tired, so to repeat all these indices, and I'm using so-called Levi-Civita notation. So summation over repeated indices. Okay? I hope you sometimes met this symbol. If we use Einstein notation, we do not write summation, and we write this. And how do I know that we have a summation? Because there are two indices repeated, one up, one down. It is a simple way for remembering that you are summing, writing short equations. Okay? Okay. Now, clearly, dl over dq dot I, we must calculate this if we want to go ahead in calculating Lagrange equations. Okay? Now, we know that the derivative of a quadratic function is a linear function. Okay? By the way, now that you are asking me these things, you agree with me that a small a of hk can be considered to be symmetric? Because the antisymmetric part of this matrix plays no role in this. Okay. If I have a1 to q dot 1 q dot q, I mean, this is linear algebra. Okay, I hope that you are simply surprised because of my Einstein notation. Plus a21 q dot 2 q dot 1. Okay? As q dot 1, q dot 2 are the same and the product is commutative, this is equal to that. So if you are stubborn and you use a matrix which is not symmetric, actually only its symmetric part works. Its symmetric part works. Okay? So in this kinetic energy, only symmetric matrices A play a role. Okay? Your faces worry me very much. This is linear algebra. Are you tired, or today you are all sleeping? Now, your faces yesterday were more active. So I hope you don't have a problem with these things. Okay? You never studied quadratic polynomials, second order homogeneous polynomials. X transposed AX, where X is a vector, A is a matrix. Okay, this is another way for writing the same thing. How do you write? Okay, I am afraid that we need to study a little bit tensor calculus. a little bit, because otherwise, I mean, it is not possible. Engineers say it is mathematics, mathematicians do not know it, so I mean, this is not possible. Okay? Look what you are doing. A1, 1, A1, 2. This you know. Okay? What you are doing here? Row times column. So you get A11 Q dot, A12 Q dot 2, A1n Q dot n. Okay? Then what you get is a column. You multiply times a row, so what you get at the end? A11 Q dot 1 Q dot 1, A12 Q dot 1 Q dot 2. So you have every pair QH Q dot H Q dot K, and you have a coefficient for every pair. Okay? Of course, it is simpler to use in this formula. So Q1 dot Q2 dot and Q2 dot and Q1 dot appear 2 times in that formula. Okay? But as the matrix A is symmetric, this is a compact way for representing a generic quadratic polynomial of second order in the variables Q dot. Okay? So this is a very standard. I mean, I am surprised. When I ask you, do you know metric spaces? Everybody said yes. Now I'm talking about something for children, second order polynomials, and you are surprised. I mean, this is worrying. So, what is the derivative of a quadratic polynomial? A linear polynomial. This you know. Okay? So, let us make the calculation. U is not depending on Q dot. So this is equal to dt over dq dot I. Okay? Now, let us do the calculation in a formal way. Okay? So I have 1/2 d over dq dot I of 1/2 ahk q dot h q dot k. I'm not writing explicitly that A depends on Q. Okay? Why? Because the derivative is with respect to Q dot, and so it is constant. Okay? So 1/2, here I have summation over H and K, which goes out. So I have 1/2 H A H K d over dq dot I q dot H q dot K. Okay? The derivative of the sum is the sum of derivatives. Okay? Now, do you know how to calculate this derivative? Easy. This is Leibniz rule. Okay? So this derivative is, so I get 1/2 AHK, then I have D over dq dot H dq dot I q dot K plus q dot H dq dot K over dq dot I. Okay? Leibniz rule. Now we have n variables. When you derive the h variable with respect to I variable, so you have the derivative of q dot 3 with respect to q dot 1. It is 0. It is 1 when you have the derivative of q1 with respect to q1. I hope you heard about Kronecker delta. Kronecker delta is delta ij is 1 when I is equal to j, and it is 0 when I is different from j. So this derivative is delta hi, and this derivative is delta ki. Okay? So this, let us go ahead. So this is equal to H, you are summing on these h's, but you have 0, 0, 0, except one h is equal to I. So you have 1/2 A I K Q dot K, which is here, and then you have summation over K. This coefficient is 0 always, except when you have plus a H I Q dot H. Okay?
But also we have minus before the sum.
Why? No, I'm simply calculating dl over dq dot for the moment. This is what I'm doing. Then we will use this in Lagrange equation later. Okay? Now, do you agree that this animal is equal to that animal? This quantity is equal to that quantity? A is symmetric. So I can write it this way. Now there is this big mystery of dummy indices. My dear friends, you cannot understand mechanics without understanding the summation, Einstein summation convention, and the indices, the symbols, I mean the symbology, the notation of Levi-Civita. Look what is this. We write it down. You have AI1 Q dot 1 plus AI2 Q dot 2 plus AIN Q dot n. Because K must have the value 1, 2, 3, and you must sum. If you have called the summation index H, what you are doing? A1 1 Q dot 1 plus A1 2 Q dot 2 plus A1 n Q dot n. It is the same. You can rename every pair of dummy indices in the summation convention without changing the value of the final result. So at the end of the story, you get these two goes away and you are left with this. So dl over dq dot I in the particular class of Lagrangians which we are considering is a linear function of the velocity, Lagrangian velocity vector. Okay? Now, d over dt, the time derivative of this, you must derive everything which depends on time. So you have daik over dq L Q dot L, calculating the derivative of composed functions, because this animal depends on Q. Okay, so you calculate its derivative with respect to Q, and then you have Q dot L times Q dot K. By the way, so-called gyroscopic effects have these terms appearing inside. But okay, but this is, in this moment, is not very important. What is important, this is a quadratic function on the velocities. Okay, yeah?
Please explain why we don't consider the minus sign of this.
Look, am I free to make a calculation before replacing it in the Lagrangian or not? I mean, this I'm calculating d over dt, dl over dq dot I. When I get the final result, I will replace in the equations. Look. I have dl over dq I minus d over dt dl over dq dot I equals 0. I am patiently calculating this. Then I'm patiently calculating this. Then I will patiently calculate this, and then I will replace everything in the equation.
Okay, but we said that L is u minus t. The Lagrangian is given by, I meant the minus.
No, the Lagrangian L is u minus t. Okay. Okay, so you want to say that there is a minus here. Okay. Okay, there is a minus here. Yeah, I agree. Okay, but it is not yet ended. Why? Because I must calculate minus AIHK Q Q double dot K. You agree?
Yeah.
Okay. So what we are discovering is that the second derivative with respect to time of Q appears linearly, and the matrix A being definite positive, it is non-singular. So soon we will discover that for this kind of Lagrangians you have that the equations are in normal form. Okay? So let's go ahead. dl over dqi is equal to, let us look at this, du over qi. So what we have at the end of the story, let us try to keep now the signs in the right shape. So if I place minus here, I get plus and plus here. Okay? So I place in this equation du du over dqi, and instead of this animal I must write this. Okay, so I write plus I q h q double dot h plus d a h over d q k. You know, I'm changing the name of dumb indices, but it is not a problem. Q dot k, Q dot h. Here I have used L and K, but there is not true problem. Okay, this is equal. Plus. No, this and that plus that. So this is equal to 0. Okay. So in mechanics there are many interesting systems whose kinetic energy depends on Q. I mean, the matrix representing the quadratic form for kinetic energy in general depends on Q. So the equation of motion is, now we can use a matrix notation, A Q double dot, which is this term, plus dA over dQ Q dot Q dot. This is a brutal way for writing that expression. Okay, they are equivalent. I write in matrix notation, and I have du plus du over dq. So if you like, equal minus du over dq. Okay. I don't know if you are starting to recognize the structure of some equations which we have met very often. Particular case in which the matrix A do not depend on Q. The matrix A is as an inverse, so you can write Q double dot equal minus A minus 1 du over dq. So what you have at the end of the story, you have that for the class of Lagrangians we are studying the Lagrangian equations are in a normal form, and you can recognize mass times acceleration equal something which in Newtonian mechanics is called force. So, as an exercise, you can very slowly but with great precision recover every equation you have already studied in physics or in rational mechanics, if you ever studied rational mechanics.
Can you repeat why we got rid of Q dot?
No, it is an assumption. There are, so look, I am studying the general class of Lagrangians made like this, where T is Q dot transposed A Q dot 1/2, and in general A is a function of Q in general. When A does not depend on Q, then the equation has this form. So what I want to say, Lagrange equations imply Newton law. Force equal mass times acceleration.
What does A actually represent? Does it have any physical A, matrix A? What are the...
It is called the matrix of masses. In the very, look, if it is diagonal, okay, we can start imagining some particular cases. Okay. Let us do this way. And that there is no more chalk. You have the general Lagrangian. Okay? Then you have the Lagrangian, the particular case L equal U minus T. Then you have the particular case L equal U minus 1/2 Q dot transpose A Q dot, and A does not depend on Q. Okay? Then let's go ahead. Consider the system of n bodies. So you have the mass M1, the mass M2, the mass M3, okay? The mass Mn. You have n bodies. The kinetic energy of this system, T, before talking about kinetic energy, which are the Lagrangian coordinates for this system? So we can say that we have x1, y1, z1, the coordinates in space of M1. Then you have x2, y2, z2, the coordinates of the second mass. Then you have xn, yn, zn, the coordinates of the nth particle. Okay? How many degrees of freedom you have? 3n. So your Q is something like x1, y1, z1, x2, y2, z2, until xn, yn, zn. Okay? You have this huge, I'm turning because I have no space. Okay? This is Q. Can you write the kinetic energy of this system? It's trivial. You have m1 x1 square plus m1 y1 square plus m1 zeta1 square, and so on. So you get a very particular kinetic energy where A is diagonal. There is no mixed term. Okay. So the matrix A in the case of n material particles is a matrix of masses of material particles. In general, one calls this matrix as the matrix of generalized masses. Which is the potential energy U in the case of n masses? If you have gravitational interaction between the masses, you have Newtonian potential energy. So you have the sum of every on every pair of m1, m2, mi, mj universal gravitational constant divided the distance between the masses. So you can write the Lagrangian of n masses interacting with gravitational force. Okay? Now I tell you the bad news that there is no available solution for this trivial problem. The problem of 3 or 4 masses has no analytical solution. You can try to only get numerical solutions. If you manage to find an analytical solution or a semi-analytical solution for the problem of n masses, even if you manage to prove qualitative properties of these, I think you get a $1 million prize, if I remember well. This is one of the problems which has not yet been completely solved. Okay?
What's the actual problem?
Sorry?
What's the actual problem?
The actual problem is to study stability, to know some qualitative solutions, properties of the solution, as it is very well known that there is no analytical solution. To get a study of this problem. Okay. So why I wanted to make you these calculations? Simply to show you that instead of postulating the balance of force, and instead of postulating that the mass times acceleration is proportional to the force, we can postulate a certain Lagrangian obtaining the same equations, but also obtaining, in general, some equations which are much more general than we expected. Because we are choosing, we started from a very general Lagrangian, we particularized making assumptions and assumptions, at the end we arrived to mass times acceleration equal force, as a very particular case. So there is a lot of space left for imagination and for inventing more general models in the framework of Lagrangian mechanics. Okay? However, following Levi-Civita, I could say, okay, I have this equation. Okay? I know there is an equilibrium equation, an equilibrium configuration for this equation. So I know that QA is an equilibrium configuration. So the function Qt equal QE is a solution of the Lagrange equation. Okay? Okay, for sake of simplicity, let us keep considering as a Lagrangian u minus t, and t, let us consider it as a quadratic function in the velocities. Okay? So for the moment we limit ourselves to this particular class of Lagrangians, which I repeat has been studied by Hamilton, has been introduced by Hamilton. Okay. So I impose that this is a solution of this equation. Okay? So I did the calculations. So I know that du over dqi. Remember me, there is plus here, right? Plus dahk over dq. Here I have q. There is I here. I erased. Can you tell me how it was? There is I here. Aik q dot l q dot k. The I is here. You have this formula or not? Plus I think this should be the equation, if you have it. Okay? What is q dot I if q of t is constant? Q dot I is 0. Q double dot I is also 0. Okay? So in this equation we are left with du over dq I in q equilibrium is equal to 0. This is a necessary and sufficient condition for a configuration to be an equilibrium configuration. A configuration is an equilibrium configuration for this class of Lagrangians if and only if the derivative of u calculated with respect to q calculated in q equilibrium is equal to 0. Okay? Now the problem arises. If I have the function u of q, I know that when QE is stationary for u, so the derivative, the gradient of u is 0, I have an equilibrium. Can I characterize the stability of equilibrium looking the phase studying the potential u? Now, I studied in detail this story about 15 years ago, and since then I have not followed all the developments. So what I can tell you is what was true 15 years ago. To my knowledge, nothing happened in these 15 years. So I can tell you that Dirichlet criterion, if QE is a minimum for u, then it is a stable equilibrium. So QE is a minimum for u implies QE stable. The big Soviet school tried to prove the vice versa. Lyapunov and many others. Nobody managed to prove the complete vice versa. If u is analytic in the neighborhood of QE, then this implication can be inverted. But up to now, it is not clear which condition is necessary and sufficient for stability. Okay, so what we can say is, okay, we limit ourselves to study the minima of energy. Okay? So now on, we will try to study this equation of motion in the neighborhood of a minimum for energy. Okay? Without trying to make the analysis too general. So, look, I am becoming probably senile. I had many chalk here and I didn't discover. I am becoming old, yes. I am also becoming senile because I'm repeating very often, always the same thing. But believe me, this is very important. I don't want to hide you anything. Human beings are very strange. I didn't stop for relaxing a little bit, so I stop a few minutes now. Usually, you tell to your child, A implies B. You tell to your child, if you get a good note at school, I will buy a bicycle for you. Your child forgets immediately the hypothesis and tells you, you promised me a bicycle. Okay? This attitude should be avoided by mathematicians. You must know that ordinary differential equations have a unique solution only, we are sure that they have a unique solution, when the function f on the right hand side is Lipschitz continuous. You cannot apply uniqueness blindly. You must be sure that your hypothesis is assured. Okay? Now, I started telling you that every Lagrangian system in the neighborhood of every stable equilibrium configurations is governed by harmonic motion. This is like a title of a newspaper. This is propaganda. Actually, what I should have said to you is, consider this particular class of Lagrangians with the assumptions which I have listed you. Consider a minimum of potential energy. Study the motions of small amplitude in the neighborhood of that equilibrium configuration. Okay? You can prove, and I will do it for you now, that all these small motions are harmonic motions. Of course, this is a beautiful result. Engineering, sciences, physics, mathematics has been greatly improved, and many scientists profited of this result. Just for telling you an application, radio. You are receiving a signal with the radio because the electric system in the receiver is governed by some Lagrangian equations which were solved for small amplitudes, and tuning the the receiving frequency, you manage to get the signal for a given wavelength. And they are exploiting the equations of the small amplitude motions for a Lagrangian system. But there are hundreds of these kind of applications. Okay, the airplane, the check of vibrations resistance of an airplane, it is made under the assumption of small deformations, small amplitude motions, and many others. Why we are doing this? Simply because we are not capable to study large amplitude oscillations. So we limit ourselves to the case of small amplitude oscillations. Okay. Even in 2019, I have a PhD student who is studying small amplitude vibrations of something. This is a topical subject now. Okay? But you should not believe that everything is linear, and you should not believe that everything is small amplitude vibrations. Why I said everything is linear, you will discover soon. But the linearity I'm talking about is this one. Okay? Okay, so let's go ahead. Maybe if you behave as good boys, we stop only 10 minutes now. Okay? Don't escape. In 10 minutes we start again.